If you have been following my series on bit manipulation, you might have already realized how important it is. You represent a number in the form of bits, and you can see that just by clearing a bit or by setting a bit, the number entirely changes. And that is what makes this concept so very important. A lot of tech companies prefer it too. So let us continue our journey. Hello friends, welcome back to my channel. And this is the part 4 of my mini series on bit manipulation. Basically, we are trying to cover all of the fundamental concepts. How do numbers behave and how can you make your code very, very performant? We are understanding how you can use bit manipulation techniques to actually perform the calculations which might take up a lot of time if done in a conventional way. We have discussed the right shift operator, the left shift operator, the logical operators, and we have even tried, how to clear a bit, how to set a bit, how to toggle a bit. So if all of that seems pretty new to you, I would highly recommend you to check out my previous videos first. Because in this video, we are gonna build on top of what we have already discussed. So if you're ready with everything, let's start. Now, before we go into further depths of bit manipulations, I would like to tell you about a concept known as truth tables. More than a table, it is actually a chart that shows all of the possible logical combinations when you are looking at several bits at once. So how do you get started with it? For example, I just have one bit available. If you have just one bit available, how many different possible combinations you can have? You can either have a 0 or you can have a 1. That is it. You cannot have any other combination possible, right? Let us try to extend this concept. Over here, now I have 2 bits. So first of all, I can write down 0 and a 1 because these are the 2 possible combinations this bit can have. But you have another bit available also. I only set the first bit right now. So the other bit can still remain 0. But if you see, these are not all the possible combinations. I can have more possible combinations when the value of this bit actually becomes 1. So if I write down 1 over here, then I can write down again a 0, 1 over here. So once again, this truth table or this chart is telling me all of the different possible combinations when I have 2 bits available. Notice that I cannot have any other possible combination. Now, similarly, let us extend our concept and look at 3 bits now. And this is where powers of 2 come in very, very handy. To determine the total possible number of combinations for number of given bits, you will use the powers of 2. When you have just a single bit, you only have 2 combinations possible. For 2 bits, 2 to the power 2, that is 4 different combinations. For 3 bits, how many different possible combinations you can have? You should have a total of 8 combinations. So let us now try to incorporate it. I have 3 bits available over here. So how many total possible number of combinations? That will be 8. So for the first bit A, I need to have 8 different possible combinations. So I can start writing them down as 0, 1, 0, 1, 0, 1, 0, 1. Because I know that there will be 8 different possible combinations. But the bit A can only alternate between 2 possible numbers, right? So these are all the possible combinations. Now look at B. To do B, what I will do is, I will write down 0 2 times, then I will write down 1 2 times. Then again a 0 2 times, and then a 1 2 times. So these are all the possible states the number B has. If you notice, this entire thing gets repeated over here. Why? Because we still have to determine the possible combinations of the bit C. And for the bit C, what I'm going to do is, I'm going to write down 0 4 times, and then I'm going to write down 1 4 times. We have 8 different possible combinations, and that is it. You cannot have more possible combinations when you're dealing with 3 bits. And notice, if you try to go any further, one of these combinations will repeat. So that is the idea of a truth table or a chart. It is giving you all of the different possible combinations that you can have with 3 bits. Similarly, you can extend this concept to any number of bits. But this chart will continue to grow larger and larger. For example, for 4 bits, how many different possible combinations will be there? 2 to the power of 4, that is 16. That means for 4 bits, you are gonna have 16 different possible combinations. And if you look at this chart, it summarizes all of the possible combinations. Notice, For bit A, I just have 0101 written all the way up till 16 times. Then when you go to bit 2, you write down 0 2 times, then you write down 1 2 times. Similarly, you keep on going. When you come to bit C, now you have to write down 0 4 times and then 1 4 times, then again 0 4 times and then 1 4 times. Notice this entire thing gets repeated over here. Why? Because the bit D was not set. But now if you look at it, I write down 0 8 times and then again I write down 0 8 times. You can naturally guess what can happen if I write down bit E over here. I will have zeros all the way up to here 16 times and then I'm gonna have 116 times. And these will be all the different possible combinations. Notice, I have covered every possible logical combination in this chart. The fun part over here is, when you create your chart like this, you are also actually representing all of the decimal numbers. How? If you notice, this particular sequence, this is equivalent to 0. This particular sequence, it is equivalent to 1. For the next sequence 1 0, that is actually 2. Similarly, 1 1 is 3. And then if you look at number 4, that is 1 0 0. So if you keep on going like this, you are representing all of the decimal numbers, and each of the decimal number can be interpreted from your particular row in your truth table. With all of this, truth table actually gives you some more information as well. For example, if you look at all of the odd numbers, do you notice something special about them? For every odd number, if you check, the last bit is always 1. And for any even number, the last bit is always set to 0. And this is a very good indication how you can determine if numbers are even or odd. And that actually helps you to even speed up your programs. For example, you could be given a list of numbers and you have to determine if the given numbers are even or odd. So over here, I have several numbers available and I'm also writing down the binary representation of them. You just have to tell me if these numbers are even or not. So what is the traditional method to do it? The traditional method, or the most naive method, what people usually do is, if your particular number modulo 2 equals to 0, then this number is even, else this number is odd. Right? This is what almost everyone has been using. But we never take advantage of the fact that these numbers are stored as bits when it comes to your memory. And what about these bits? If the number is odd, then this last bit will always be 1. If the number is even, this last bit will always be 0. And that is true for every number available. So what does that tell you? If you can just check this last bit, then you can easily determine if the number is even or odd. So instead of my traditional method, can I do something like this? If my number and of 1, if this is equal to 0, then my number is even, else my number is odd. Will this work out? Yes, because when you do this particular calculation, what is actually happening? For each of these numbers, you are trying to AND it by 1. All of the remaining bits will be 0. And when you do an AND operator on each of these numbers, what do you get? Since all these other numbers are 0, they all turn out to be 0. But 1 and 1, since they both are 1, you will land up a 1 over here. 1 and 1, this will be a 1. 0 and 1, this will be a 0. And 0 and 1, this will be a 0. In case of even numbers, the result will be 0. In case of odd numbers, the result will be 1. Because all of the other bits are already set to 0. So they are all going to become 0. So just by doing this, you can also determine if the number is even or odd. Now you might ask, okay, what was the error in my previous method? Well, there is no error. Even if you use the modulo operator, your program will be as efficient. But when you're talking about competitive programming, even all of these small things matter. If you are using the bitwise operators to determine if a number is even or odd, it will be much faster than when you're using the modulus operator. And it also depends how many times you're using the operation. For example, if you just have to use it one time in your code, then it doesn't really matter. But think about a case when you're given thousands of numbers and you have to do the modulus operator on each of them. All of these small increments compound up and they end up taking a lot more time than using the bitwise operator. And in competitive programming, that is what makes all the difference. So next time, whenever you have to determine if a number is even or odd, try using the bitwise operator instead of the traditional method. And you might have already seen that the number 2 is very, very interesting. You used it while creating truth tables, and it is also being used to determine how to convert numbers to binary and how can you convert them back. Well, let us explore an even more fascinating part about the number 2. And this time, we will be looking at powers of 2. Over here, what do I have? I have the binary number 10, then I have 100, then 1 triple 0, then 1 and a 4 times 0, and then 1 followed by 5 zeros. If you convert all of these numbers to decimal, you will end up with numbers like these. And what are these numbers? 2, 4, 8, 16, and 32. But they are also known as powers of 2. So over here, I can say that this is actually 2 to the power of 1, this is 2 to the power of 2, then 2 to the power of 3, then 2 to the power of 4, and then 2 to the power of 5. So once again, this is an interesting concept about binary numbers and powers of 2. Notice that if I have one 0 available, that is 2 to the power of 1. If I have 2 zeros available, this is 2 to the power of 2. If I have 3 zeros available, this is 2 to the power of 3, and then so on. You get the idea. If you have to represent 2 to the power of 7 in binary, how do you write it? It is very, very simple. Just put the number 1 followed by 7 zeros. Actually, this concept is not just limited over here. If you also notice, what is 2 to the power of 0? 2 to the power of 0 is actually 1. And what does that mean? 1 followed by 0 zeros. So this holds true even over here. But why are we discussing all of this? If you notice, all of these binary numbers, they have all of the bits as 0, except for one bit. So I can safely say that if I have a binary number in which only one bit is set, and that is the leftmost bit, then for sure that number will be a power of 2, correct? If I have any other bit set, if I have this bit as set, then this number will not be a power of 2. Based upon this idea, we can actually look at a problem statement. You are given a number and you have to check if this given number is a power of 2. Now, in your problem statement, you could be given a decimal number or you could be even given a binary number. But you don't have to worry about anything when it comes to bitwise operators, because bitwise operators will also work upon your decimal numbers, because in the memory, everything happens in bits. So let us say I am given this particular problem statement. I am given some numbers and I have to tell that if these numbers are powers of 2 or not. When you look at the binary representation of these numbers, without doing any sort of calculations, you can now easily tell if this number was a power of 2 or not. Notice, only one bit is set over here, so this should be a power of 2. Multiple bits are set over here, so this cannot be a power of 2. Once again, only one bit is set, so this is a power of 2. And over here, multiple bits are set, so this cannot be a power of 2. Logically, we have now found out the solution. If I only have one bit set, then this number is a power of 2. So if I have to write some kind of a logic for it, if I am able to remove the last set bit, then if the number becomes 0, it is a power of 2, otherwise not, correct? You can now understand that it will be correct to say that if I remove the last set bit and then whatever number I get, if that is 0, then it is a power of 2, correct? So in my first test case, if I change this to 0, the entire number becomes 0. So this is a power of 2. In the second test case, I change this to 0, but this is not equal to 0. So this is not a power of 2. Over here, I remove the last set bit. This becomes a 0. So this is a power of 2. Over here, I change the last set bit and this is not equal to 0. So this is not a power of 2, right? So this logic is actually correct. But how do you use bitwise operators to remove the last set bit? This is something which we had discussed in our previous lecture, that if you take the number and then you AND it by n minus 1, that will help you to clear the last set bit. So basically what I'm gonna do is I'm gonna do 32 and 31. Similarly, 57 and 56, 16 and 15, 20 and 19. Now, if I represent these numbers in binary, 31 will be 1, 1, 1, 1. Similarly, 56 is going to be 1, 1, 1, 0, 0. 15 is going to be 1, 1, 1. And 19 is going to be 1, 0, 0, 1, 1. When you do an AND operation, what will happen? This entire thing becomes 0. What about this? 1 and 0, this becomes 0. And all of the other things remain same. So the result I get is 1, 1, 1, 0, 0, 0. Hence, this is not a power of 2. What about the next one? I get a 0 over here. So this is a power of 2. And what about this one? 0 and 1 will give me 0. 0 and 1 will give me 0. 1 and 0 will give me a 0. And I have 1 available over here. And again, this is not equal to 0. So this is not a power of 2. So my solution becomes very, very simple. I can just say if n and n minus 1 equals to 0, then this number is a power of 2. Otherwise, it is not. Notice how efficient this method is. If you had gone the traditional route, you will start a for loop and then you will keep on dividing by 2, keep a track of 100 different things. And what about if you had to do it for 1,000 numbers? This will end up taking so much time, correct? Now, let us take a pause over here. Try to understand and go through all of the concepts that we have discussed so far. Tell me any problems that you face. Just try to understand how powers of 2 work and try to represent these numbers as binary numbers. Try to understand what happens when you do n minus 1 and represent that number. Try to understand what happens if you do n plus 1 and you get a particular binary number. Just try to perform logical operations between n and n minus 1 and similarly n and n plus 1. Just doing all of these operations are gonna give you some generic patterns. You are gonna see, okay, these bits get set or these bits get cleared. And these are the little nifty tricks which you can always use to make your program even more efficient. If you're liking these kind of tricks, a subscribe to the channel will be very, very helpful, as this really keeps me motivated. And I would also like to give a huge shout out to all of the members who support my channel. You guys really are the rock stars. And as a member, you do get priority reply to your comments and early access to new videos as well. Also remember that now you can schedule one-to-one session with me and we can discuss about almost anything. Stay tuned for my upcoming videos where we are gonna look at some more generic problems which you can solve efficiently using the bitwise operators. So stay tuned for my upcoming video. Until then, see ya.